So we continue, having looked at the reactions of ions in solutions. We want to look at the theories that are behind these reactions. So we're looking at theories of ions in solutions. We're going to look at the bond model. These are the theories: dielectric saturation, discontinuous theories, relaxation or asymmetric effects, electrophoretic effects, Debye-Huckel-Onsager equation, and we look at the deviation from Debye-Huckel-Onsager equation. Macron assumed that the solvent is a continuous dielectric. Now we will still see a diagram of dielectric. It's just like where you have, somebody moving in the class where you have two lines made up of positive and negative charges. In this case now, a boy who is moving in between a line made up of boys and girls by the side, there's every likelihood that his friends will be on that line. So as he's moving, he will be attracted by those his friends. So those dielectric, that is the human beings now on that line, will not allow him to move straight because of the attractions. Born obtained an expression for the work of charging the ionic sphere. So the ion that it moves, charging that ion, remember conductance, when the ion moves from one point to the other, we talk about conductance, we also talk about conductivity. Now this work is equal to the Gibbs energy increase during the charging process. So the work done in charging the ionic sphere itself is equal to the Gibbs energy increase. Let the radius of the sphere be equal to R. Let the final charge be ZE. Then we assume that the charging process is affected by transporting from an infinite distance small increments of charge equal to the Q. Q is the charge or the quantity of charge. If at a particular distance the charge on the sphere is Q, then the work done in transporting the increment through a distance dx is given by this. That's the work done, equation 1, the W. In fact, this is an example of inverse square law. If you look at this, we are seeing Q dq dx over x squared. The whole of this 1 over 4 pi epsilon 0 is a constant. So we're saying that the change in the work done is directly proportional to the charge and inversely proportional to the square of the distance. That is Newton's law of gravitation. This is playing out here still a kind of Coulomb's law, Newton's law. In this case now we're looking at charge in place of mass of either the planet or the earth or whatever we're looking for, where x is the distance and epsilon 0 is the permittivity of vacuum and epsilon is dielectric constant or relative permittivity. Therefore, the work done in transporting the increment from infinity to the surface of the sphere is done by integrating equation 1. Remember, when we integrate equation 1, we now get this. This is 1 over 4 pi epsilon 0, epsilon is a constant. And then when we integrate, we now have equation 2. And since we say this is equal to the Gibbs, change in Gibbs free energy, now this work is equal to reversible work, which is this, where the maximum charge is ZE. So we replace and we'll have this. So equation 3 represents a non-PV work, the electrostatic contribution, that is the Gibbs energy we mentioned. Therefore, we replace W reversible by Gibbs energy for electrostatic contribution. So if the charging process is carried out in vacuum, then epsilon will be equal to 1. The electrostatic Gibbs energy now changes to this. So epsilon is 1, and of course this is now in vacuum. Therefore, the electrostatic Gibbs energy of hydration is equal to electrostatic energy minus that of vacuum. So these two equations, that is this, equation 4 minus equation 5, and we'll have equation 6. So when for water at 25 degrees C, epsilon is 78. And if we solve equation 6, we will get this value, where relative permittivity of water is equal to 78. And there could be saturation of that dielectric. Remember, if we say we have dielectric constant, so the dielectric can be saturated, and when it is saturated, we'll see what makes it saturated. Now, one Weybourne theory of ions in solution was improved upon is to consider how the effective dielectric constant of a solvent varies in the neighborhood of the ion, based on the fact that, one, the dielectric behavior of liquid is related to the orientation of the liquid. Now, when you have very high field strength, the molecules become fully aligned, and there won't be no further orientations. And at that point, you say we have dielectric saturation. And in fact, when that happens, then we start looking at what happens to water. A plot will give us how the variation of this electrostatic Gibbs energy varies with the distance. Now, these continuous theories, we have looked at continuous theories. Let's look at this continuous theory. And one of them is the Debye-Huckel theory of conductivity. Now, the long range and strength of the Coulombic interaction between ions means that it is likely to be primarily responsible for the departures from ideality in ionic solutions, and it dominates all the other contributions to non-ideality. Remember, our Arrhenius law of dissociation and Oswald's law of dilution apply to only weak electrolytes. If you remember when we talked about Arrhenius law of dissociation and Oswald's law of dilution, it applies to only weak electrolytes and not to strong electrolytes. That means weak electrolytes are not completely dissociated in solution. Of course, we should know that. As concentration increases, the conductivity of weak electrolyte decreases rapidly. Remember our diagram we drew where we had a graph, weak electrolyte would drop drastically while strong electrolyte would drop slowly. For strong electrolytes, however, we observed the following. They are fully dissociated, yes. The molar conductivity decreases as concentration increases, but not as drastic as weak electrolytes. The decrease here in molar conductivity with increase in concentration, though significant, is much less than that of weak electrolyte. That's what we just said. Now, Peter Debye and Eric Huckel put forward a mathematical explanation of the behavior of strong electrolytes. According to them, the decrease in molar conductivity of strong electrolytes is due to mutual interference of ions, which becomes more pronounced as concentration increases. So as concentration increases, the number of ions also increases, and then you have mutual interference of the ions. For instance, in sodium chloride, solid sodium chloride, there is a regular array of sodium and chloride ions. The distribution of chloride ions is such that each sodium ion has 6 chloride ions around it, if you remember your crystallography. In solution, the interionic distances are greater and the distribution is not as regular, but near the sodium ion there are more chlorine or chloride ions than sodium ions. You can see what happens in solution. According to Debye and Huckel, the small amount of irregularity which exists in this solution of strong electrolyte affects the conductivity of the solution. So because of this, when it dissolves, now there is irregularity which now affects the conductivity of the solution. Of course, if you look at this conductivity, initially the ion in solution is stationary and the ion atmosphere is symmetrical. When the ion is stationary, all the attracted opposite ions will be symmetrical. But when we apply potential, positive ions move to the anode. Of course, positive ions will move to the cathode. Since it takes time for this relaxation, now what we are saying is that when it is now moving, it is no longer symmetrical. It will now drag that ion atmosphere with it. So this symmetry of the ion atmosphere will have an effect of dragging the central ion back. So as it's dragging it forward, the ion atmosphere will also be dragging the central ion backwards. The more concentrated the solution, the closer the surrounding ion are to the central ion and the greater the drag. And the influence of this is what we call relaxation or asymmetric effect. There is no longer symmetry around the ion atmosphere, so we have asymmetric effect or relaxation effect. The second factor that retards the motion of ion in solution is the tendency of the applied potential to move the ion atmosphere itself. Look at this. Instead of moving only the ion atmosphere itself will be moving. Now imagine it becomes a load. It's just like when somebody wants to drag you alone and you put your hands to 6 other persons and the person is now dragging you plus 6 other persons. That will be very heavy. Ions are attracted to solvent molecules mainly by dipole forces. Therefore, when they move, they drag the solvent with them. The ion atmosphere has a charge opposite to that of the central ion. So if you have something like Cu2 plus ion, which is positive, if it is an aqueous solution, then it will be attracting OH minus ions from the water molecules. This means that the central ion has to travel upstream and hence move slowly than if there were no effect of this kind. And this effect is what we call electrophoretic effect. Therefore, the final equation of the Debye-Huckel theory allows us to estimate the thickness of the ion atmosphere, which is given by equation 8. All this here is to explain the components of this equation. 1 over K is the thickness of the ion atmosphere. That's what we're looking for. Dielectric constant, relative permittivity, electronic charge, Boltzmann constant, and so on. Therefore, according to this equation, the thickness of the ion atmosphere is inversely proportional to the root of the concentration. The atmosphere moving further from the central ion as the solution is being diluted. The second one after Debye-Huckel equation is Debye-Huckel-Onsager equation. Now, as you see, it means that we have an addition by Onsager. And what happens here is Onsager now put up, a proposal by considering the Brownian motion. Debye-Huckel was looking at the motion of ion in straight form in solution. But actually, when these ions are in solution, they don't move straight. There will be zigzag Brownian motion. Remember demonstration of Brownian motion in secondary school, where we look at the zigzag motion. So when these ions are in solution, they now have incorporate this zigzag motion. That's what Onsager incorporated in the Debye-Huckel theory or equation, and we obtain the Debye-Huckel-Onsager equation. And this equation is given by equation 9. And then in simple case where Z plus Z minus are 1, that is 1:1 electrolyte, equation 9 will now simplify to equation 10. So the Debye-Huckel-Onsager equation is based on the assumption of complete dissociation of the electrolyte. Of course, complete dissociation means we are talking about strong electrolyte. Now, in a situation where an electrode cannot be described as strong or weak, the equation must be modified by a factor involving the degree of dissociation. For weak electrolytes, the ions are generally so far apart that the ion atmosphere is so diffuse. Then this makes the relaxation and electrophoretic effect very negligible, thereby making the Debye-Huckel-Onsager equation unnecessary. So for weak electrolyte, the ion atmosphere is diffuse because it's not completely dissociated. So the Debye-Huckel-Onsager equation no longer come to play. Now for univalent electrolyte, we can simplify the Debye-Huckel-Onsager equation and get equation 11. In fact, this is where we get the equation of plotting molar conductivity against concentration, and we can obtain our molar conductivity at infinite dilution. That diagram we use for molar conductivity at infinite dilution. Now there are some deviations from Debye-Huckel equation. The equation is obeyed satisfactorily at low concentration. Deviations occur for high concentrations. Even in non-aqueous solvent, agreement with the equation is only at very low concentration, and deviations occur at higher concentrations. The equation is obeyed over a wide concentration range. If the solvent has high dielectric constant, solvent with low dielectric constant and those that are non-hydroxylic cause deviations from Debye-Huckel-Onsager equation. And again, one of the ways in which electrolyte failed to obey this equation, this discrepancy was attributed to ion pairing. There's what we call ion pairing. This is a situation where in solution, ions come together from time to time. So they are no longer free. They pair up in solution from time to time. To form ion pairs which do not contribute to the transport of electric current, low dielectric solvents favor ion pair formation. This is because such solvents give rise to higher electrostatic attraction between ions. Okay, thank you very much. We've looked at the Born model, dielectric saturation and discontinuous theories, relaxation or asymmetric effect, electrophoretic effect, and of course the Debye-Huckel-Onsager equation and deviations. Thank you very much. I hope to see you in the next class.